Now, we have talked about continued fractions before. Do you remember what they are?
Well, it's just like, say, it would be like a fraction that would go on for a very long time, like 1 plus 2 over 1 plus 2 over 1 plus 2. And it would keep going down like that.
Yeah, that's right. It's a fraction that sort of descends. The denominators have fractions, and the denominators of those denominators have fractions.
Yeah.
All the way down. So we're going to write root 2 as a continued fraction. And does anybody remember the funny named procedure named by my high school math teacher?
Split, flip, and rat.
Split, flip, and rat. That's the procedure we're going to follow.
Okay.
So split means we're going to split into the integer and non-integer part. So what does root 2 equal?
It's about 1.414.
All right, so it's 1 plus something, and that something is root 2 minus 1. It's 1.414, so it's 1, that's the integer part, and the non-integer part is root 2 minus 1.
Okay.
Okay. Flip means we take the non-integer part and we put it in the denominator. 1 over root 2 minus 1.
Okay.
Okay. So when you have a fraction in the denominator, what do you do?
You have to rationalize that.
Well, sorry. Why is this 1 plus root 2 minus 1 equal to 1 plus 1 over root 2 minus 1?
Well, if you have like a double 1 over, you can always flip the bottom so it's up at the top.
Yeah. When I divide by a fraction, which I'm doing here, it's the same as multiplying by its reciprocal. And now that's what the flip means. And what does the rat mean?
You have to rationalize this part.
Rationalize.
Okay, and how do I rationalize that?
Well, you can multiply by root 2 plus 1. You need to get rid of the root 2 on the bottom.
Okay, so here I multiply by root 2 plus 1, root 2 plus 1. And this becomes a difference of squares.
Yep.
So what am I left with on the bottom?
You have to 2 minus 1, so
Yep.
1.
Yep.
And then on the top is just root 2 plus 1.
Okay, so this ends up being the same as 1 over root 2 plus 1. And now I just continue. So what is going to be the integer part of root 2 plus 1?
Root
So-
1.
What?
1.
Well, you got 1 and then you have a 1 in here, so you have 2.
2.
Yeah, so this is root 2 is about 1.4, so root 2 plus 1 is about 2.4. So this is 1 plus 1 over 2 plus, what's the fractional part?
It's root 2. It's 1 minus root 2 minus 1.
Right, root 2 minus 1. Hey, that's the same thing we saw up there. So now I can flip it. Which is the same as root 2 plus 1.
And then this will keep going down forever.
So what is the continued fraction for root 2 equal?
So it looks like it's 1 plus 1 over 2 plus 1 over 2 plus 1 over ...
Does it ever stop?
No.
Why not?
Because root...
What, big brother?
Well, root 2 is not. You can't fully rationalize it, ever.
Yeah, but what about this procedure shows that this is never going to stop?
Well, when you do the procedure, you end up in a loop.
Right, you end up in a loop.
So it'll just continue down.
It'll just continue down.
You do the same procedure every time, and you always have a root 2 at the end of that procedure.
Yeah, and then we can start looking for approximations to root 2 by sort of studying this fraction. First we can just look at 1. That's an okay approximation to root 2. Then we can look at 1 plus a half, which is 3 halves. And then we can look at 1 plus 1 over 2 plus a half, like that. Do you know what that simplifies to be?
It's 1 2/3.
I don't think it's 1 2/3.
You can multiply by 2 here.
Well, what is 2 plus a half?
2 plus it's 5 halves.
Okay, so we got 1 plus 5 halves on the bottom.
1 over 5 halves.
Okay, what is 1 over 5 halves?
2 fifths.
Okay,
So 1 and 2 fifths.
which is how many fifths total?
That, let's see, 7 fifths.
Yeah, so 7 fifths is our next approximation. And we can go all the way, we can just keep following this and we can get these numbers.
Better and better approximations.
We can get better and better approximations of root 2. By the way, 7 fifths is equal to 1.4, which is, what we were saying, root 2 is pretty
Good.
close to. So Mathematica has a couple functions that do this for us. So we're going to do this with a couple different numbers and just see what these approximations start looking like.
All right, cool.
Okay?